So let's start by talking about the exam itself in terms of its construction. So I wrote the test this morning. On the test itself, there are going to be 17 questions. Now that is a bit deceptive because after the 12 multiple choice sections, those 5 short answer questions are going to have multiple parts to them. So while there are only 5 of those questions, there are going to be the bulk of the time that you spend in the exam itself. None of the multiple choice questions involve any kinds of calculations. They're all concept. With maybe one exception, I think I have one molar mass question in there where I give you a compound and ask you the molar mass of that compound. Aside from that, none of those questions are anything you would need your calculator for. The only thing that we really need our calculators for is the stuff out of chapter 7. So if I look at the exam coverages here, you can see I've given you percentages of content based upon those 85 points. And so you can see that just under 45% of those 85 points are out of chapter 4. And so in here, we are talking about looking at things like nomenclature, looking at Lewis structures, resonance structures, bond polarity, electronegativity. Again, one of the things I told you to focus on, something that you definitely would want to have knowledge of, is of the concepts on here, there are some that we definitely spent more time talking about than others. The majority of the content in that chapter was here in the covalent bonding and the Lewis structures, and then kind of getting into the ideas of polarity because we use them to muon as bridge concepts in chapter 5. So that is where I would spend the majority of my focus. Now there are going to be some nomenclature questions in there. Nomenclature is technically part of chapter 4. You had a proficiency about nomenclature already. So you should be well prepared for that already. But the majority of the focus is here in Lewis structures themselves. Chapter 5 and chapter 6 make up about a little less than 30% of the exam. And so in here, we're looking at things like molecular shape, geometry, the Vesper theory stuff, looking at molecular polarity, hybridization, valence bond theory. You know, pretty much all of this stuff all comes from the same central concept. So you can see that out of one question, I could ask you about any of these things. And it piggybacks off of Lewis structures as well. From a Lewis structure, we can determine all of our Vesper information. From that Vesper information, we can determine everything about molecular polarity, valence bonds, sigma bonds, pi bonds, hybridization, and so on.
Are you going to have a sheet with the Vesper theory?
Yes, you are still going to have access. You will be given 3 reference pages. Okay. A periodic table, the equation sheet that's been on every single quiz thus far, and that reference page which has all of the different hybridizations, bond angles, and everything else on it.
So we don't need to like memorize those?
No, you didn't need to memorize it for the quiz. I'm not going to make you memorize it for the exam. So that should take a little bit of the burden off of you. Because now it becomes a matter of, do you know how to use the table, as opposed to, do you know how to go, okay, I've got 5 bonds and a lone pair, that's an octahedral, what is it? It's square pyramidal, but you don't need to know that. You can just follow the chart on that.
Wasn't that like, say, given us like silicon
What do you
Like,
mean?
like it's neon 3S to SP2.
Electron configurations were in chapter 3, so they would not be part of this exam. Out of chapter 6, you're going to be talking about intermolecular forces. So can you identify those 4 primary types of intermolecular forces and where they apply? Do you know the difference between London dispersion and dipole? Do you know the difference between dipole-dipole and ion-dipole? Can you use those intermolecular forces to explain physical properties? So for example, if I gave you 2 compounds, could you tell me which one is more viscous? Or could you tell me which one has a higher boiling point? Or could you tell me if the 2 substances dissolve in one another? These other things, these are vocabulary terms. You're probably not going to see a whole lot of them other than maybe in the multiple choice. The other possibility for a question would be a phase diagram. And remember, that's that pressure versus temperature graph, where we've got the 3 different phases mapped out. And really all that you could be asked of those is similar to what you saw in the quiz.
Like
Yeah.
where something was, like
Yeah, so
solid speed or.
yeah, so can you tell me which region the solid region is? Can you tell me which region the liquid region is? If I give you a phase diagram and point to a spot on the diagram, can you tell me what phase of matter to expect? That's about as far as our interpretation of phase diagrams would end up going.
So that would be on the multiple choice.
More than likely, yes. Yes, what about it? We did. Viscosity is directly related to the strength of the intermolecular force. So the stronger the forces are, the more viscous the substance is, because they stick together more. The stronger they're attracted to each other, the more sticky they are as a substance. So if I have something like diesel fuel, which has very little viscosity, its low viscosity is directly related to the fact that it's just hydrocarbons in there, and they only have London dispersion forces holding them together. Whereas if I look at something like molasses, where I've got a very high concentration of sugar, which has hydrogen bonding, and water, which has hydrogen bonding, those are going to be very, very attracted to each other, and that makes them stick together more. They're in general more viscous. They're more sticky. They're less likely to be able to pour out or flow easily. Chapter 7 is basically a 2-concept chapter. We've got balancing and identifying reaction equations, and we've got stoichiometry. And that stoichiometry does include limiting reactants. Now, from that perspective, I will caution that if you go to Blackboard and you download the practice test here, the one thing that you're not going to find on this practice test is anything from Chapter 7. And that's because this particular practice test was done in a semester where we only had chapters 4, 5, and 6 on that particular unit. Now, part of the review session today is we can do as many or as few stoichiometry problems as we need. And as you're preparing for that part of the exam, that's exactly what you're going to need to do. It's just get in somewhere, find as many stoichiometry problems as you can handle, as you can eat, and do as many of them as possible. So before we get into practice test itself. Are there any particular concepts off of the review page here, or just in general, that we want to go over, just as this is something I'm struggling with, and I need to know before we leave that I can do this. Kyra? Okay. All right.
I think that'd be a good one.
Okay, so let's do some stoichiometry. All right, for that, it's not going to let me preview it, is it? Okay, let's try it this way. I had to do that. SmartWork won't let me access any of the questions until I get the assignment in A. This is one of the wonderful little quirks of SmartWork. Okay, let's just go through a couple of these and we can address them as they come. All right, so we've got butane. Butane is vaporized and then burned to create carbon dioxide and water. First thing we need to do is write a balanced chemical equation for the combustion reaction. Second thing we need to do is figure out how much carbon dioxide is made from this combustion. So this is a combustion reaction. So I've got butane, C4H10, reacting with oxygen, because that's what happens in a combustion reaction, is we have something burning in oxygen. And it's going to make carbon dioxide and water. First task is to balance this. If I balance it, I end up with a 4 for the carbon dioxide, a 5 for the water to give me 10 hydrogens. This in turn will give me 4 times 2, which is 8, and 5 times 1, which is 5, for a total of 13 oxygens. And so we get faced with the dilemma of I either need to put a fraction, 13 halves, to give me the coefficient for the oxygen, or if that doesn't suit me particularly well, I can take all of these numbers and multiply them by 2 to give me whole number ratios, which is what they're ultimately looking for here. And so 8 of these, 10 of these, 13. This is how we end up with the balanced chemical equation. Now, I don't know if it affected you who are in this room. A number of you got that first question wrong on the quiz on Monday. And a lot of you had made the mistake of getting into what I almost would have to describe as rounding, where you got to that point here where it came out to 13 halves or 6 1/2, and you rounded it up to 7 and you called it good, and it wasn't actually balanced as a result. If you find yourself in that particular scenario where the only way to balance it is with a fraction, with a non-whole number, multiply everything by 2 and see if that solves it. In this case, that's exactly what happened. So now that we have that, our next step is to actually do the stoichiometry. Stoichiometry that we're interested in here is we want to convert 3.89 grams of butane into grams of carbon dioxide. So I'm starting with grams here. I need to go to grams here. Following the mole map, I'm going to have to go through moles. To connect all those two dots to each other. So my first order of business, I need to convert the grams of butane into moles of butane. My second, I need to turn the moles of butane into moles of carbon dioxide. My third step is to convert the moles of carbon dioxide, moles of carbon dioxide into grams of carbon dioxide. Where do I pull these numbers from? I need to find molar masses, so I need periodic table. The molar mass of butane, 4 carbons, 4 times 12.01, 10 hydrogens, 10 times 1.01, for a grand total of 58.14 grams per mole. Molar mass of carbon dioxide, 1 carbon, 12.01, plus 2 times oxygen, 16, is 44.01 grams per mole. The only other thing I'm missing is the mole-to-mole ratio, which again comes from the balanced chemical equation. It's 2 to 8. So now I got to put all the pieces together. 1 mole of butane is 58.14 grams. I'm going to get my grams of butane to cancel out. 2 moles of butane is 8 moles of carbon. That's going to get the moles of butane to cancel out. 1 mole of carbon dioxide is 44.01 grams.
Yeah, but whenever you're multiplying all that out, you always multiply top first and then you divide afterwards.
So yeah, you're going to multiply by everything in the numerators. You're going to divide by everything in the denominators. It technically doesn't matter what order that you do it in, because multiplication and division are essentially the same operation. But that is what you're going to do. Now, for convenience sake, or kind of keeping it straight sake, yes, I usually tell you to multiply everything first, then divide everything in the bottom second. Technically speaking, since it's the same function though, you could do them in any order. The properties are transitive. So 3.89 multiplied by 8, multiplied by 44.01, divided by 58.14, divided by 2. I get 11.8 grams of carbon dioxide. So if I punch that in, it's not going to let me check because I'm not in the student view, but Otherwise, I would have felt really foolish. But that's the process. That's what you would ultimately have to do. Yeah, we're close enough. I mean, we can do it. Just put 2.81 instead of 3.89. See, I know what I'm talking about sometimes. Okay. For the good and the order of everybody, let's do another example. Just to that one? Okay. We elicited a strong response here.
This one was, the next one down is one that.
Okay.
Do you have a question like that? Maybe.
No. No, but we can show off here a little bit. All right. Uranium minerals found in nature must be refined and enriched before the uranium can be used. One procedure begins with natural uranium dioxide and reacts it with hydrofluoric acid to form uranium fluoride, uranium 4 fluoride, which is then converted to UF6. The question is, how many kilograms of HF are needed to completely react with 5.26 kilograms of UO2? So,
Basically, it's the same, but they're giving you a not ounce, but they're giving you an equation and you have to balance this out.
so in the case of part one here, part one's just straight up stoichiometry. We've got UO2, we're trying to figure out how much HF. The equation is balanced. So all we need to do is that. Now for this one, the trick to it is in the combination. If I add these two equations together, the UF4 ends up canceling out. UO2 plus 4HF plus F2 makes UF6 and 2 H2Os. That would be the balanced chemical equation that we ultimately work from to solve the second one, to get the correct mole ratio. You could have figured it out.
Well, we tried to substitute it, and I guess it didn't work.
So what you would have ended up doing, what you could have done is you could have converted the UO2 to moles of UF4,
That's what we did,
and then use the moles of UF4 to calculate moles of UF6. Since it's a 1-to-1 ratio there, that additional mole-to-mole step would have been 1-to-1.
Well, doesn't it have to do that first step? I mean, that's the first one that has to happen, the second one, right?
Yes, it does, but, and here's the important but, all of the UO2 gets turned into UF4.
Right.
So if I figure out how much UF4 there is, I can then convert the UF4 into UF6. I don't need to convert to grams in every case. I can convert to moles, and then convert the moles of the one thing into the moles of another thing. So if you didn't know to add them together, what you would have done was you'd have taken your grams of UO2, converted it into moles of UO2, converted that into moles of UF6, or sorry, UF4. Use the second equation to convert them into moles of UF6. and then taking that one to grams. All right, well, let's try it out. All right, so let's start small. How many kilograms of hydrofluoric acid are necessary to react with 5.26 kilograms of UO2? All right, 5.26 kilograms is the same thing as 5,260 grams. So we're just going to save ourselves a little bit of a headache there. 5,260 grams of UO2. We're going to go from grams of UO2 to moles of UO2. Moles of UO2 to moles of HF. And then since we're going to grams, moles of HF to grams of HF. And we'll just convert it to kilograms at the very end. Our mole-to-mole ratio here is 1 to 4. Our molar mass of UO2, uranium, element number 92, is 238.03. Each oxygen is 16, so 16 times 2. 270.03 is our molar mass. Molar mass of HF. Hydrogen is 1.01. Fluorine is 19. So we're talking 20.01 grams per mole. So plugging in our values, 1 mole of UO2 is 270.03 grams. My grams of uranium dioxide cancel. It's a 4-to-1 ratio of hydrofluoric acid to UO2. And 20.01 grams in every mole of hydrofluoric acid. 5,260 multiplied by 4, multiplied by 20.01, divided by 270.03 to 3 significant figures is 1,560 grams of HF. We divide that by 1,000, 1.56 kilograms is our answer. All right, questions with that one? That one seemed to be the more straightforward of the two. All right. The second question, how much UF6 can be produced from that many grams of uranium dioxide? So here we have 2 possible processes that we could use. Like I said, we can go the combination route, where we take our grams of UO2, turn them into moles of UO2, use the combined equations to give us the moles of UF6, and then convert that to grams.
So when you combine equations, you just add up all the reactants and then, put down all the reactants and
Yes, so what happens is, if we were to add these two together, I know it's kind of obscured by the work here, what we would find is that their UF4 becomes more or less a de facto spectator ion. It gets canceled out because it's on both sides.
That's what I was gonna ask, if you just cancel out the spectator ion.
Yeah, it's not the same thing. This idea of equation adding and cancellation is something you'll see more in Gen Chem 2, for those of you that move on to that particular course. But the idea is kind of the same, is kind of similar to when you add together equations, things that are common on both sides can get canceled out. And so since UF4 was common on both sides, we can cancel it out because it becomes more or less what we would call an intermediate
And you
product.
just bring down all your reactants.
Yeah.
Bring down all of your products.
Everything on the reactant side gets added together, everything on the product side gets added together, and you cancel out anything that is. Now, for those of you that are looking at doing the half reaction method for redox, that's the same kind of thing that you're going to do in that method. Is you'll have your oxidation half reaction, your reduction half reaction, you add those two together to get the overall reaction itself, and you cancel out anything that is common on both sides. So it is the same kind of process. It's just not something we've talked about explicitly yet. But that would be the way that you could do it.
So you can just bring down the rings of UO2 that you have up there, and the moles of UO2 that you have up there.
Yeah, so from that perspective, if I were to add these up, then again, it would be UO2 plus 4HF plus UF4 plus F2. That's all four of my reactants. Plus UF4, 2 waters, and UF6. That's all 3 of those products. And then what we would see is that UF4 is common on each side, so it cancels out. The net result is that we can see that there is a 1-to-1 relationship between the uranium dioxide and the UF6, which kind of makes sense. It's the only uranium product. So all of the uranium in the product is coming from the only source of uranium in the reactants, the UO2. So armed with that knowledge now, we start with our 740.5 grams of uranium dioxide. We have the molar mass. So step 1, 1 mole of UO2 is equivalent to 270.03 grams. We've just determined that every mole of UO2 is 1 mole of UF6. The only step that's left is to convert the moles of UF6 into grams. For that, we're going to need to calculate again. Uranium is 238.03. Each fluorine is 19, so 19 times 6, 352.03. Yes, 352.03. So now we go about the calculation. 740.5 times 352.03 divided by 270.03. This one would be 4 significant figures because we started with the measurement of 4. And 2 4 significant figures, we get 965.4 grams of UF6.
Okay, these weren't as bad as I thought they were. I was freaking out about it.
We got it.
Good job.
I should teach a class on this.
You should. I mean, dang. Become a doctor in it too.
All right. So that's kind of your base level stoichiometry. The only thing that we really haven't talked about out of stoichiometry is limiting reactants and percent yield, which
I was gonna ask.
we can certainly go ahead and look at those. We have to change.
So the identifying the big reactants, isn't that like your soluble salts or?
No, so identifying limiting reactants is basically doing what we just did
Oh, and whichever one's left, yeah.
and making
Okay.
and making sure we know how much is, you know, which one runs out first, how much gets produced as a result. So something along these lines. Where I've got something like potassium superoxide, KO2, reacting with carbon dioxide to make potassium carbonate and oxygen. Question is, how much oxygen could be produced from 2.43 grams of KO2 and 4.60 grams of CO2? Now, the process that you undergo here is exactly the same as the process that we've been doing the last 2. The only difference is we have to do it now twice, once for each reactant. Okay.
So basically, you have grams and you go with grams to moles and the mole ratio, and moles back to grams of what you're finding.
Right.
Is that gonna be for every single one? Like for this exam?
More or less, yes. I'm going to give you one of the products, and so I mean I'll tell you straight up, this is going to be one of those combination kinds of questions where I give you something like this, and I say determine the limiting reactant and the theoretical yield of oxygen. And so I'm giving you an end point. I'm giving you somewhere to anchor your calculation and say, okay, this is where I want you to end. That way you've got a little bit less variability in terms of, there are lots of ways to determine limiting reactants. You can turn the mass of one reactant into mass of another reactant in a pair. You can, use them each to figure out how many moles of product are going to be made. And you can choose whatever product you want. By giving you something to shoot for, I'm limiting those options. And so if you've thought about it and if you've prepared yourself appropriately, then you'll do exactly what I tell you to do. That means you only have to do two calculations. One that turns the KO2 into oxygen, the other one that turns the carbon dioxide into oxygen, and figure out which one makes the lesser amount. So let's go ahead and get some molar mass quantities out here. So that when the time comes, all we need to do is put in the right values in the right places. So for KO2, potassium is 39.1. Oxygen is 16, and there are two of them. So we've got 71.10 grams per mole. For carbon dioxide, we've calculated this one a number of times. You probably have a devoted memory by now. 44.01 grams per mole. For oxygen, 16 times 2, 32.00 grams per mole there. So now we've got our molar masses. Let's highlight our mole ratios as well. So for the first one, KO2 is going to be 4 to 3. 4 KO2 to 3 oxygen. CO2 to oxygen is going to be 2 to 3. And so now we've got all of the pieces and parts. We just need to do the actual calculations to determine what the limiting reactant is. So let's start with the superoxide, KO2. 2.43 grams of potassium superoxide. We're going to go from grams of KO2 to moles of KO2. The next step is going to be to turn the moles of KO2 into moles of oxygen. And then finally, we're going to turn the moles of oxygen into grams. Okay, now I got to put the right numbers in the right places. 1 mole of KO2 is 71.10 grams. My orange ratio, 3 oxygens for every 4 KO2s. And there are 32.00 grams of oxygen in every mole. Do the calculations, 2.43 multiplied by 3 multiplied by 32 divided by 71.1 divided by 4, the 3 significant figures, I get 0.820 grams of oxygen. Now, I don't know if that is the limiting reactant. I don't know if that's the theoretical yield. I don't know anything at this point other than 2.43 grams of potassium superoxide makes 0.820 grams of oxygen. To answer the actual question, I've got to compare it to the amount of carbon dioxide. So I start with my 4.60 grams of carbon dioxide. I'm going to convert those grams of CO2 into moles of CO2. I'm going to turn the moles of CO2 into moles of oxygen. And I'm going to turn the moles of oxygen into grams of oxygen. I get the numbers that I need. 1 mole of carbon dioxide is 44.01 grams. My ratio, 3 to 2, 3 moles of oxygen for every 2 moles of carbon dioxide. Last step is exactly the same, 32 grams in every mole. 4.6 times 3 times 32 divided by 44.01 divided by 2. I get 5.02 grams of oxygen. So which is my limiting reactant? Yeah, my potassium superoxide is definitely the limiting reactant. And my theoretical yield? Theoretical yield would be one of these two numbers. Be the 0.82.
Yeah.
Yeah. Yeah. We haven't even gotten into percent yield yet. Remember, stoichiometry just gives us theoretical yield.
So it'd be the 0.820.
Yeah, it'd be the 0.820. Now, if we were asked a percent yield question here, that 0.820 would be the numerator, or excuse me, the denominator, you're right, the denominator of that fraction. So percent would be the actual yield divided by 0.820 grams times 100%. Now on your quiz, you were given the percent and you had to solve for the actual yield. Yeah, you would apply the percentage to the theoretical yield. So if it was 80%, you would multiply 0.820 by 80% by 0.8.
Are you going to ask about how much excess reaction is left over?
I thought about that particular question and decided against it. Primary reason was I thought it would take too much time. And on an exam that already has a number of Lewis structures that you have to draw and interpret, and a limiting reactant problem that you have to go through, it didn't seem like the best use of our time.
Well, thank you.
I debated about it. I went back and forth.
Flip a coin for it. Don't let it go, kid.
No. I decided to come down on the side of you guys liking me rather than throwing daggers at me on your way out of the class. So. Okay, so let's put chapter 7 away. We've got about 35 minutes left. I think we're at the point where we've done a number of problems there. I think we're starting to get it. Let's look at something else.
Okay.
Okay.
All right.
All right, let's get something that resembles back on task here. Given the time here, what do we want to look at out of those first 3 chapters? The key to this practice test is on Blackboard, and it's something that you can download already. I actually made the mistake of never hiding it. It's right there.
So like ionic bonding, so we kind of go over that.
Okay, what do you mean?
Like, number 3. Yeah. Like the types of bonding and the differences between them, we like just go over that a little
Yeah.
bit.
Yeah, okay, so when it comes to those different types of bonding, remember there are 3 primary types of bonding. There's ionic bonding, covalent bonding, and metallic bonding. Now, metallic bonding is easy to figure out because it only occurs in metal samples or mixtures of metals. So the only place where we're going to see metallic bonding is in like lead or silver or iron or aluminum, or if I have a mixture of those things. You know, like I have brass, I have copper and zinc together in the same mixture. Those are going to have metallic bonds. Covalent bonding, that's where we have electron sharing. We can identify electron sharing based upon the chemical formula. The chemical formula that we're going to base it on is I'm looking for non-metals. Non-metals share electrons with other non-metals. That is what is the hallmark of a covalent bond. So even though things like HCl, which we know is an acid, and we know that when we dissolve it in water, it's going to break apart into ions. As a compound itself, it is covalent. Those are electrons that are shared between the hydrogen and the chlorine. The one that isn't is lithium fluoride. What makes lithium fluoride different? Lithium's a metal, fluorine is a nonmetal. Ionic bonding tends to happen between metallic elements and non-metallic elements. So that would be the ionic one. All of the other ones are going to be covalent because they're all non-metallic. Hydrogen and oxygen are both non-metallic elements. Nitrogen and oxygen are both non-metallic elements. Carbon and hydrogen are both non-metallic elements. Hydrogen and chlorine are both non-metallic elements. They participate in covalent bonding. We can draw Lewis structures for all of them that show how they share electrons with each other. For lithium fluoride, we can draw a Lewis structure for it, but it's going to be a lithium ion and a fluoride ion. We're going to talk about how they're attracted to each other electrostatically as opposed to through a sharing of electrons.
On the, like when you use the Roman numeral, that's something I calculated for them.
Okay,
2, 3, 4.
the Roman numeral in a compound name indicates the charge on the metal ion. So when we say that we have manganese 4 oxide, that means that we have the manganese 4 ion, Mn plus 4, and the oxide ion, O negative 2. The correct formula for charge balance, I would need 2 of these to balance out the positive 4 charge. MnO2 would be the correct formula. So anytime you see a charge in Roman numerals or a number in Roman numerals on a nomenclature, That tells you two things. First of all, it tells you that it's ionic. Second thing it tells you is that that is the charge on the metal ion.
So it would be.
It would be MnO2. So similarly, if we had something like gold 2 chloride. Gold 2 refers to the oxidation state of the gold, which is positive 2. Chloride has a set charge, -1. AuCl2 would be the correct formula for the compound.
So chloride is always -1?
Chloride is always -1. Really, the only ones that don't follow their periodic trend are the ones in the middle. The ones in the middle, the transition metals, those are the ones that we tend to see the variability for, and that's why we use the Roman numerals to help us differentiate between them. So the Roman numerals help us tell the difference between iron 2 and iron 3, between copper 1 and copper 2, between lead 2 and lead 4. Lead and mercury, yeah. Lead can be either 2 or 4. Mercury can be either 1 or 2. And with mercury, that one's the most difficult because we've got mercury 2, which looks pretty normal. And then we've got mercury 1, which is anything but. Now, the reason that one is mercury 1 is because we've got two, or we're referring to it basically by its oxidation state. We've got 2 mercury atoms sharing a +2 charge, which means that each one is +1. Now that we've talked a little bit about oxidation numbers, the tie-in between the Roman numerals and the oxidation states makes a lot more sense because that's essentially what they are. We think of the charges and oxidation states as being the same thing.
So number 7, what is the total charge of the carbon atom? That's the structure for carbonyl sulfide.
So for that one you have to draw it. If you drew it, you would end up here. 6 for the oxygen, 4 for the carbon, 6 for the sulfur, 16 in total. Remember, formal charge is equal to valence electrons minus dots minus bonds. For carbon, we've got 4 valence electrons. It has no dots on it and 4 bonds on it. Remember, we count each bond individually. So it'd be 0. Now the trick here, I pulled this one actually off an ACS exam. The trick for most carbon compounds, formal charge is usually 0 for carbon. Rare cases where it's not, but for the most part, carbon forms 4 bonds, and when it forms 4 bonds, it has a formal charge of 0 because it can't form 4 bonds and have dots. It's not capable of breaking the octet rule.
Isn't the hybridization theory based around carbon?
What was that?
The hybridization theory, is that based on what carbon has?
really. Our ideas of Vesper theory come from electron minimization, the minimization of repulsion. Now, a lot of carbon compounds are part of that, but no, it wasn't based solely on carbon. Now, you might be thinking of our entire basis of mass is based off of carbon.
Now, this is YouTube video. It's a really good video, but in a sense, that's what starts out as how the hybridization theory comes from carbon and its properties of body.
Okay.
It's a good video for explaining.
You'll have to send it to me. I'm curious.
I didn't have an answer sheet, but for the life of me, I can't figure out number 8, the next one.
Okay.
I mean, I know it's not A, B, and C.
Okay, it's actually, it is B.
B?
Uh-huh. Now, we didn't talk too much about this, this particular concept. We didn't talk too much about this particular concept, but the idea is when chemical reactions take place, you're going to break a whole bunch of bonds, and you're going to form new bonds. The energy that is either absorbed or released in that chemical reaction depends upon the relationship between what bonds were broken versus what bonds were formed. The more energetic the bonds are that are broken, the more energy has to be put into the reaction to get it to go. The more energetic the bonds are that are formed, the more stable they are, and therefore the less, the more energy they release as they form bonds. So bond breaking is always an endothermic process. It requires energy. Bond forming is always an exothermic process. It releases energy. The more energy that is released, the more exothermic, the more energy is released. So the better that the product bonds are, the more energy gets released as a result. So the answer there is actually B. D and E are wholly untrue. D says that bond energies and lengths are not correlated. They vary independently. We saw, that was one of the things that we did talk about a lot, was the relationship between bond length and bond strength. The shorter that bond is, the more secure that bond is. The longer it is, the easier it is to break. And E says that bond energy and bond order, that is the number of bonds, are unrelated to each other. Well, we saw that one as well. A triple bond is way stronger than a double bond, which is way stronger than a single bond. So of the concepts that we did talk about at the end of that chapter 4, those two concepts there at the end were the things that we focused the most on. And so if you do see a question like that on Monday, it's going to be in that line of thinking, not in terms of overall energetics, but more in terms of what are the relationships between bond energy, bond length, bond strength, bond order. And those are the things that you were quizzed on in that chapter 4 quiz as well, where you had to click on which bond is the strongest, which bond is the weakest, which bond has the most energy, the least energy, that kind of thing.
How do you put large, like the various, like you did in the lab,
it won't be as elaborate. You know, I'm not going to give you 4 or 5 things to compare like we did in that skill builder, but I might give you a couple of things to compare. okay, here is methane and here is octane. Which one's going to have the higher boiling point? Why is it going to be that case? Well, in the case of methane versus octane, octane's got 8 carbons in it. The methane only has 1. Octane's going to have a higher molar mass, so it's going to have greater intermolecular forces. It's going to boil at a lower temperature. Or, I'm sorry, it's going to boil at a higher temperature. It's going to have a lower vapor pressure. So, no, you're not going to have to do large-scale kinds of comparisons like you did in the skill builder. It'll be on a smaller scale if that kind of question comes up. But keep in mind, I can ask that for any of those colligative properties. It could be viscosity, it could be solubility, it could be vapor pressure, boiling point. Not going to have room to ask you for all of them, but it could be any of them. So be prepared for all scenarios. Okay. All right, so these kinds of questions you shouldn't have to worry about in the multiple choice. Because again, they're a little bit more involved. You gotta draw all these. One of the big reasons I put these kinds of questions in that particular group's exam was this was drawn from an ACS practice exam.
So we won't have to worry about it.
Not until the final. The final exam is a standardized exam. It's all multiple choice. When the time comes, we'll get ready for it then. I'll teach you some ways to do these kinds of problems a little bit more quickly. But no, for Monday, we don't have to worry about that. That being said, we have to start with water. So with water, I have a steric number of 4, which would be sp3. What I'm looking for is I need something else that is sp3. And so from that standpoint, I should be able to right away eliminate CO2 and CS2. Because we know based on carbon, carbon does not do that kind of bonding unless it forms 4 bonds to 4 elements. So those ones are out. Same thing with OCS, because you're going to have that carbon in the middle and oxygen and sulfur on either side. It really comes down to the sulfur dioxide versus the ammonia. In the sulfur dioxide, you end up with this structure. In ammonia, you end up with that structure. This one is sp2, because I have 3 electron groups. This one is sp3, because I have the 4 electron groups, the 3 hydrogens, and that lone pair. Ammonia is your correct answer. So the only way to really do it is to draw everything. But like I said, if you know a couple of key features in particular about how carbon does what it does, the only way that you can get sp3 with a carbon center is to have it bonded to 4 other elements or 4 other atoms. And B, C, and E don't fit that description. So you could eliminate those for that reason. But you also had to know that water was sp3 as well. That was the other trick to that one.
So like where is ion dipole first? Ion has to be not necessarily polar and not polar, right?
So in order to have an ion-dipole interaction, you have to have an ion, and the sodium ion will be playing the role of the ion in this particular play. and you have to have a dipole, which means you have to have a polar molecule. So really what this question is asking is which of those 5 is polar?
You're on 12.
Yeah,
I
12.
thought you were talking about 11. It'd be C.
Yeah, okay, so yes, number 11 is D. We did just define that. Number 12 is C. C is your polar molecule here. How do we know it's C? Okay, we're looking for asymmetry, right? All of these compounds have symmetrical tungsten. They're all carbon and hydrogen, or carbon and only chlorines. That hydrogen represents that one thing that is different, that is going to make chloroform asymmetrical and therefore polar. Everything else is a whole bunch of the same. And again, for polarity, we're looking for different. We're looking for non-conformity, something that is sticking out as unique about that molecule, either in its formula or in its structure. So in this case, chloroform is the only one that could have fit that description because of that hydrogen, creating that element of disparity, that element of asymmetry. All right, any of these jump out that we need to go over?
So no question on 15 on the exam, right?
So if there is a phase diagram question on the exam, it will be something like 15. What is the answer to 15?
C.
Yeah. Remember, phase diagrams, the top region here is the solid, the middle region is the liquid, the low region is the gas. So the crosshairs there in the solid region makes C the correct answer.
Okay, on the short answer for number 2.
Okay, so this is where we're talking about lattice energy. What we want to look for is charge and then size. The ones that have the biggest charges are also going to have the strongest forces. And if we have a tie in charge, then we're going to start looking at size. Compactness is going to be a crucial factor. The more we can concentrate that charge into a smaller space, the more attractive the forces are going to be. So, which one of these 3 has the strongest charge? The aluminum oxide, Al2O3, that is going to have the strongest charge because the positive 3 on the aluminum. Which one is going to be the weakest? 1 plus charge, and that puts calcium oxide square in the middle. And then as far as the reasoning goes, that's where you use those arguments of charge and size, or in this particular case, we really didn't need to talk about size at all. Aluminum's has the biggest charge, and that's going to be the biggest attraction. Yeah, with a +3 charge is going to be the most attractive because it's got the largest quantity of charge. Calcium would be next with a +2 charge. Sodium would be last with a +1 charge.
So they don't always balance out with the zero.
How do you figure?
So. Okay, so.
Got a +1 for sodium and a -2 for oxygen. I've got 2 sodium, so that's 2 and 2. So no, they're all balanced. They're all balanced in charge. Really can't be an ionic compound without that. Otherwise, it'd just be an ion. If there's not a balance of charge, that means that there's leftover charge. That means that you've got an ion.
Can you just multiply the charges?
That's
Which one's the biggest?
that's more or less what it is. So this is based on Coulomb's law. Coulomb's law says that you multiply the charges and divide by the distance between them. So from that standpoint, if you multiply these, you get a -2 here, -4 here, -6 here. That is going to have a much bigger impact than the radii. So we kind of framed it in terms of Coulomb's law, but I didn't state it explicitly because with that equation, you get a tendency to want to do the calculations, to do the math, and it's usually just easier to qualitatively compare the charges to each other rather than worry about their product. But yes, if I had something else in here, and I don't do this, but if I was asked to compare sodium oxide versus lithium sulfide, we'd have a little bit of a problem there because our values are the same. And we'd have to go to sizes, and it'd be a tough comparison to make. And that's why I don't do it. If there's a question of this kind, it's going to be straightforward, either in terms of you're going to have something like this, or if it is a tie, then there will be a clearly defined difference in size. Potassium is bigger than sodium. Sulfur is bigger than oxygen. That whole compound is bigger than the other compound. So this one is going to be stronger in its attraction than this one, because those ions are closer together. All right, that's about all the time I have. Thanks for coming. And I'll see you on Monday, I guess. See you tomorrow. Yeah, that'll be fine.